Great. Well, thanks for the introduction, Peter. Thanks for coming. One of the things that I think is really important as this field evolves is that we get more and more people interested, and we talk externally about the field. So I do this a lot. My background's in hardware and software for quantum computing, so I'm very much from the field. But I think it's extremely important that as the field develops, we get more and more types of people looking at problems. So that's one of the things I'm going to use as a lens here as I talk about quantum programming. I want to ask one quick question before I start, though, just to gauge the audience a little bit. Who here knows what a Hadamard gate is? Okay, pretty cool. Great. So it's a basic unit. It's a basic instruction in quantum computing. So a lot of the things in this talk are introductory. So they don't assume that you know anything about quantum computers. You need to know a little linear algebra. But I want to show you how I talk about quantum computing to people who don't have a lot of background already. So even if you know some of the introductory material, I hope you find it useful as a way to talk about it in an honest way. The first thing for us to think about is why should we do this in the first place? And even though we have so much technology around and it's so effective, without us really knowing it, we're being held back from solving some of our biggest problems. And while quantum computing is not the answer to everything, there's hope that we're going to be able to solve some more of the problems that are out there than we can solve today with today's technology. So the themes of the talk are to talk a little bit about why one should program a quantum computer, and if I convince you that you should do this, how you might go about it today. And the field's moved very, very rapidly, so how you'd go about it today is very different than it was 6 months ago or 8 months ago or a few years back. The first thing to remember is that classical computers actually have fundamental limits. Everything from transistor scaling problems where there's both physical limits, and you can't just keep increasing the resolution in how you make transistors. You're going to eventually run into the fact that you have single atoms to deal with, to the fact that it's very economically expensive to continue to make smaller and smaller transistors. It now costs billions of dollars to make a new fab. So there's physical limits to Moore's law, and there are also economic limits to Moore's law that we need to remember. You might ask, well, why can't we just make more processors instead of making better processors? And this doesn't work as well. There are some algorithms that are embarrassingly parallel that will scale, but others will not. And you'll be stuck. Amdahl's law is an example of this that applies to lots of types of problems. And the third area is in energy consumption, which people don't think about sometimes. So recently in the US, it was announced another $1.8 billion are going to go into the exascale computing project, right, to get to the next size in supercomputing. That plant, that computer is going to have its own power plant. And it's pretty serious stuff. So, and it's also serious not at the macro scale, but at the micro scale. As we increase the density of transistors, the temperature goes up, and you start to melt the materials you're using on the chip. So there's some real fundamental issues about just continuing along the classical computing path. But there's a lot more that we want to do. There's a lot of problems that we can't solve. Everything from being able to design drugs better on computers through simulation. It takes 10 years and $2 billion to develop a drug. We want to be able to design new kinds of technologies using better catalysts, things like organic solar cells, organic batteries, and obviously artificial general intelligence. Some people will tell you we'll get there in 5 years with regular computing, but I think that might be a bit of an outside bet. So given that this is the state of affairs, why should we build a quantum computer? Why is this a good way to start tackling new types of computing problems? I think there's really 3 reasons: new power, new opportunity, and there's a fundamental reason, too, that shouldn't be lost. So the basic power inherent in quantum computing comes from an exponential law. And this is something that doesn't come into play in other kinds of post-Moore technology, but it's that if you have n quantum bits, called qubits, then it requires 2 to the n of them to simulate it. So there's this exponential overhead in exact simulation. So this compute unit, your Commodore 64, can exactly simulate 10 qubits. The larger, beefier AWS instances can simulate 30 exactly. And if you had the whole global cloud dedicated to this problem, you could exactly simulate 60 qubits. And so this, you guys are pretty expert. You've heard this and seen this a lot in the media. And it's not as simple as this. There are more details. And so what I'm going to do, you've seen this before, but I want to give you a different model. I want to go one level deeper and talk a little bit about a better way of thinking about quantum computing than just this kind of exponential scaling idea. But before we do that, we have 19 qubits. They're available. They've been up since December. You can program them today. This is kind of the state of play. But the thing to remember is that these are not 19 perfect qubits. These are smaller. They have some noise. There's errors that you have to deal with. So you have to program them in a different way than you would program these perfect qubits. So what's the better model? So I like to think about it in this way. So if you have n qubits, then every time step, which in our systems, the superconducting systems we work with, is about 100 nanoseconds, then you're doing an exponentially large complex matrix multiplication. And there are some crucial details here. This is an extremely powerful thing to have at hand. If this is 100 qubits, then you're multiplying 2 to the 100 by 2 to the 100 complex matrices in 100 nanoseconds. So here are the crucial details. You have a limited number of multiplications. So due to the fact that each one of the multiplications you make, there's some error, you can only make maybe hundreds or thousands due to noise. And this is in kind of how we project out where we'll be able to get in the next few years. Another crucial detail is that you can't multiply arbitrary matrices. So you need to construct matrices out of tensor products of basic gates, out of basic matrices that we have, and there's some structure there. An interesting fundamental problem is to ask, what is the structure of the matrices that we can easily construct with a polynomial number of quantum operations? But to abstract that high, you can't do arbitrary matrices. The last thing is that there's kind of a small I/O. So even though there's a huge complex model inside of a quantum computer of 2 to the n by 2 to the n complex numbers, your I/O is limited. So I'd like to share with you this model that I think works pretty well for thinking about quantum computing, which is the kind of big memory, small pipe model for quantum computing. And this works, I think, as a better way to explain what quantum computers can do than saying, exponential scaling. And that's, okay, we have fundamentally some large resource, but there's limited input and output. So at the end of the day, we can put in some maybe polynomial number of bits, which describes the quantum program that's going into the computer. We have an extremely large model space in the middle, and then we get out some small number of bits. And so the problems that fit into this domain are ones that are interesting in the near term for quantum computers. And I'll talk a little bit about some examples. So in this context, there's a wide range of stuff we've been looking at and think are very exciting. There's everything from machine learning problems to things in optimization to simulation. I mean, broadly, it's three categories. Those are the three categories that we think about. So the key characteristics of these are that they're types of applications where approximate solutions are still useful. There may be better approximations than we have today, but they don't have to be exact. And this is an important characteristic of applications for near-term computers, which still have errors and noise in them as we build them. I mean, one day we'll have big, perfect quantum computers, but before we have that, we'll have the smaller ones that have some limitations to them. The second point is that all of these types of problems fit into this big memory, small pipe kind of model. So I'll maybe give you an example. So one of them is in computational, or maybe alternative energy or catalyst design. So if you're trying to design a catalyst, it's pretty easy to write down the structure of the molecule. And it's pretty easy to get out the amount of information you want. Maybe you just want the ground state energy or the structure of the molecule when it's in its ground state. So it's a small amount of information in and a small amount of information out. But to model that problem is actually an exponentially large problem to do it exactly. So problems that are like this fit really, really well in quantum computing in the near term. Quantum simulation might sound like it's a bit of an esoteric thing for someone to work on, but it's really, really not. So when we try and design molecules, we're very, very limited today. So in the last 100 years, we've been able to use computers to design airplanes so that we can go from the Wright brothers to jet engines. And a lot of this has been done because we know the physics, but we can simulate and optimize on computers. If you contrast that to a molecule that we all take for granted to make fertilizer, and it's called the Haber-Bosch process. We use a catalyst that takes nitrogen out of the atmosphere, turn it into ammonia. And we've used the same process for 100 years, even though 1% to 2% of the world's energy every year goes into this process. And one of the reasons we can't design a better molecule is that we can't do simulation-driven design on computers today. So quantum computers, when we get them up and going, have this promise to open up some things in terms of material design, technology design, and enablement that we don't have. So I definitely don't think that the simulation application is one that's esoteric. So what's not on here? Breaking encryption. Obviously, this is the thing that got everyone initially interested in quantum computing in the 90s. But it's a problem that requires exact solutions. You can't approximately factor. There's no notion of that, right? 21 is 10 and 3. It's not approximately 8 and 4 as the prime factors. So not only is this not, in my opinion, an interesting business case, doesn't really help the world, it's also not the kind of thing you can do with the computers we're building in the next decade, I would argue. We're going to be doing all the stuff up here for maybe 10 or 20 years before we even start running or testing the algorithm. So what's the state today? So the state of play is that processors have actually started to scale up. So we had a period of initial excitement in the early 2000s when people started to build a few types of systems in specific modalities, but there have been changes in scaling. There have been engineering changes in how we make hardware that have allowed people to scale up much more quickly. So the two systems that are publicly available now are our 19-qubit system and IBM's 20-qubit system. And then, of course, there are more proposed systems in much larger scales. This threshold here that I plotted is kind of approximately that same number of the limitations you have if you try to simulate a quantum computer using a regular computer. It's maybe about 60, maybe it's 70. It's sort of in this generic range. So once we push through that limit and we have chips that are around that scale that have that number of qubits, you start to have a resource that can do something no other computer can do. And this is moving quite quickly. There's also been a lot of investment from academia, government, and this has happened across the globe. So this chart is actually from 2015. And so since then, there's been even more growth. And by like my rough count, there's something like approximately $300 million in global VC investment in different kinds of technology. This number might be a little bit off. It's just kind of my rough estimate. So with this new power, there's a lot of new opportunity. But quantum computing isn't just about the technology. So I actually got interested in quantum computing because of the relationship between physics and computer science and how they relate to each other. And because this is so fundamental, it isn't just about one piece of technology. So every time we understand more about physics, we get a new kind of industrial revolution. So we understood thermodynamics and mechanics, and we got the first industrial revolution. We understood Maxwell's equations, and we got electronics. And we've known about quantum physics for, 110 years. And it makes a subtle play into how we build tech today. So transistors wouldn't work without quantum mechanics. But we haven't really embraced what that physics can do and what it would mean to build technology out of it until today. And so this is a picture of one of the quantum computers that we have in Berkeley and that we built. So it's not just about one type of tech. It's not just about a quantum computer. Eventually, it's going to be about a whole raft of quantum technologies that do all sorts of things. So the second point is to return to this fundamental idea. So I think quantum computing really changes the relationship between physics and computer science. I bounce back and forth between these two fields. You might intuitively think, and I think a lot of people do think, that we have an idea of what computers should do. And we have mathematical proofs that we think they could perform. And if only physics didn't limit us from what we could build. And it's not actually that way. It's actually that the physical reality is more creative than we are and more unintuitive. And so quantum computing says that if you look at reality and try to build computing systems, then you might find something very different. And I think this is a very deep point about the relationship between mind and body and physics and computation. I think that the realization, at least for me personally, that that quantum mechanics isn't just a theory of physics, but is also a theory of information and a theory of computation, was pretty pivotal. And in my opinion, whatever theory comes after quantum mechanics is also going to be a theory of information in that same way. And so what this is saying is that physical phenomena apply to information and computation as well. Things like superposition, being in two states at the same time. No cloning, which says that there's no way to exactly copy any hunk of quantum memory, which implies something about a uniqueness of systems and a uniqueness of information in quantum. And teleportation, right? These are interesting concepts at an abstract level, but now we can turn them into technology that can do things. So I hope I've convinced you that because there's so much new power that might be available, and there's new opportunity today, and there's some fundamental interesting facts about quantum mechanics and quantum computation, that you might want to program a quantum computer. So how would you actually go about doing this? And as we get into this, please just ask any questions you have. The first thing to take away is that quantum computers are not just a hunk of quantum memory. It's not actually just a quantum computer. It's a quantum processor and some set of classical processors. So over here is a picture of our 19-qubit chip that we fabricated in California, designed and fabricated there. And it goes here in the bottom of this refrigerator unit. And then there's this whole large control rack that's actually controlling what happens on the chip. And there's CPUs and FPGAs in there. And when you target a quantum computer, and this is what you're looking at here, this whole system is one of several quantum computers we have, you're talking to both those kinds of processors. And there's a lot of reasons to do that. So the model you should have in your head is that near-term quantum computing is what's called hybrid quantum classical computing. And so here you have, at an abstract level, like a CPU with some number of bits and a quantum processor with some number of qubits. And the platform that we built, which is called Forest, which targets these kind of systems, is optimized for this kind of computing. And it's actually built around an instruction set architecture called Quill, which is a shared memory model, where you have these 2 bits of memory, and it talks explicitly about how instructions can have information work back and forth. And if you want to read more about that, there's a white paper. The spec is open, and it's really the base layer for how we do programming. I'll talk a lot more about it in this talk. The reason why we do this is that you can use the CPU to compensate for limitations in the quantum processor. So even though there's noise in the quantum processor, you can optimize around that noise. I'll talk more about that. So what does quantum programming look like? If you pull out kind of the abstract fundamental pieces, what you're doing is you're building up some program, which is some instructions that happen on the quantum memory. They're quantum instructions. This quantum processor applies those instructions, and at the end of the day has a probability distribution inside of it that you sample from. And you come back and get some answer. And you can do this iteratively in some kind of procedure. So I hope you all indulge me. I have a 1-slide intro to quantum computing, which has sometimes worked well and sometimes not worked well. But the way that I like to introduce quantum programming or quantum computation, so the basic mathematical framework, is with a halfway step. So we start with bits, and then we step to probabilistic computation, and then we step to quantum computation, which you can actually see as a natural generalization, and in fact a much more powerful generalization of probabilistic computing. So the first bit to look at is what is a state? What is the state of a single unit of computation in each of these frameworks? So in classical computing, it's a bit. In probabilistic computing, it's also a bit, but it's a probabilistic bit. And so in this example, I have 2 real numbers that sum to 1. And my number A describes the probability of my bit being in 0, and B describes the probability of it being in 1. So I can represent a classical probabilistic bit on a line, where I'm either between 0 and 1, depending on an exact coin is in the middle. In the quantum case, I generalize this. So instead of having a real vector, I have a complex vector. So I'll have my alpha and beta instead of A and B. And alpha and beta are complex numbers, so that their magnitude squared sums to 1. And I interpret it in a similar way. So the square of alpha gives me the probability of it being in 0, and the square of beta gives me the probability of it being in 1. So this gives me a different picture. So let's think a little bit about what it is to represent a totally unbiased coin. So in the probabilistic scenario, there's just one place on the line. There's only one way to represent this, and that's by setting A and B both to 1/2. In the quantum case, I've actually got a lot more options. So all of these examples as complex numbers will all act like an unbiased coin. 1 over the square root of 2 is 1/2, but so is I over the square root of 2. And in fact, this totally generalizes, and there's an infinite family of exact coins for a single quantum bit. And so that means that when I try and represent this, I'm actually not looking at a line for a qubit. I'm looking at a sphere. This is called the Bloch sphere. And all the representations for this coin are that infinite 1-parameter family around the equator. So at the top, I have where alpha is equal to 1 and beta is equal to 0. And then there's all these other kinds of combinations that live as states on this sphere. So even when you look at a single unit of computation, there's a whole bunch more states available in the quantum example than there are classically. This is part of what gives you some computational advantage. The next thing to look at is to generalize to multiple kinds of units. So in the normal example, you get a bit string instead of a bit. For probabilistic bits, you get something called a stochastic vector, which is just a list of probabilities, one probability for each bit string. So it's just a distribution over bit strings. And you can compose that by taking individual probabilistic vectors and taking the tensor product of them together. And that gives you the state of that probabilistic system. Quantum is exactly the same thing. So in the quantum case, instead of having a probability for every single bit string, I've got one of these complex numbers, which is called an amplitude. And instead of it directly representing the probability, it squares. So the amplitude, so alpha x squared, gives me the probability of a bit string. And in just the same way, if I take the tensor product of multiple qubits, I'll get the state of some quantum register or some set of qubits. So now that we understand memory, we should look at operations. So in the classical case, we have Boolean logic and gates. In the classical case for probabilistic bits, we operate with stochastic matrices. So you can think about transformations on a register of probabilistic bits as matrix multiplications, where every one of these matrices has some normalization condition, which ensures that if I start with some probabilistic vector and I multiply by this matrix, then this probability vector also has, it's a probability vector. It sums up to 1 again. So there's just some normalization condition. So computation probabilistically is you start with some state vector, you multiply by a matrix, get another state vector, multiply by another matrix, and continue on. Quantum is the same thing, but generalized. So in the quantum example, we have a different normalization condition. So instead of this one, we have what's called the unitarity condition, which says that my matrix U that I multiply this vector by, its complex conjugate transpose has to be its identity. And what that does is it means that if I sum up all the squares of the complex numbers here, I'll get 1. And if I obey this condition and I multiply by a unitary matrix, that condition is also true here. So I'm sort of preserving the probability mass. The last thing is how do we think about composing operations? So in the regular case, we don't just have Boolean logic. We've got gates, specific XOR, and. In the probabilistic bit case, we can take a single matrix that applies to a few probabilistic bits, and we can tensor product it with others to get a larger operation. And it's the same thing in the quantum case. So you actually build up full computations by tensor products of all of these different types of unitary matrices. So there's a couple ways of going between these frameworks. So if we want to go from probabilistic bits to regular bits, we do sampling. So we look at distribution, we sample to convert between these data formats. To convert between quantum and probabilistic data, we can use the Born rule, which is this example that I've been bringing up. You just look at the amplitudes, and that gives you some probability distribution back out, so you can always convert. And you can also convert directly from quantum bits into regular bits using the process called measurement, which I'll talk about a little bit more. So how do you actually program this? That's kind of a basic mathematical framework. And I'm going to use Quill, this quantum instruction language that we've developed, as the example. So in Quill, you have quantum operations, and each one is an instruction. In this case, you just give the name of the instruction, and then you tell what quantum bit to operate on. So you think of some list of quantum bits indexed from 0 to n, and those are the ones to work on. And in fact, in Quill, you always start in what's called the 0 state. So the example we'll do here is a two quantum bit example. So if I have 2 quantum bits, and they're both 0, I represent that as one of these wave functions, so a list of complex numbers, each of which squares to the probability of that outcome. So this squared is 1, so I'm certainly in the ground state when I represent the state of the system like this. So I'm going to apply some operation. In this case, there's this thing called an X gate. It's this matrix as a quantum knot. And if you multiply this vector by this matrix, tensor producted with the identity, so you get the right sizes, then you just flip the 0th qubit. So in Quill, there's as indexing from the right to the left. So the qubit all the way to the right is the 0th qubit. And there's a great paper about why we chose exactly this convention. It is well thought out, and if you want to know more about that, I can tell you more about it later. There's also other kinds of operations that you can do. So you don't just have to do exact ones that do exact flipping. You can do things like the Hadamard gate. So this creates a superposition. So if I take this matrix and multiply it, tensor product it with the identity and multiply it by this vector, then I end up with this vector back, which says I'm in some combination of these two states. So the qubit on the left is always 0, and the qubit on the right is kind of in between. And there's also operations that happen on multiple qubits at the same time. So if these are examples of bit flips and generalized bit flips, these are your examples of like an AND gate, where you have 2 inputs, and in our case, 2 outputs again. You never go from 2 inputs to 1 output. And if you apply this to this state, you just multiply the matrices, then you get this interesting combination, which is entanglement. And what does this actually mean? So this means that this state says that half the time I'm in both qubits are 0, and half the time both qubits are 1. But what I do know is that they're always the same. So if I look at any qubit separately, it looks like an unbiased coin. But if I look at them together, I know they're always the same. And this is what entanglement means. So there's other kinds of operations you can do. So in addition to just operating on the quantum data itself, you need to get the data back out. So how do we move quantum data back into classical data? In Quill, this is represented by a measure instruction. You pass in some quantum register, and then you have some classical bit register. So remember, the model is we've got some list of quantum bits and then some list of regular bits. So you can think about measurement as doing some data conversion, or just changing the data type. But it operates in an interesting way. So if I measure this, it's half 0 and half 1, and there's some 50-50 branching. So either I end up in this outcome, where both qubits are back to 0, and my classical bit register is itself 0, it starts in 0. Or I end up here, where both qubits are 1, and I have deposited the quantum information from the measurement of the quantum information from qubit 0 into the classical register 2. So I flipped that one because this one's in 1, so I should flip it back to 1. And I knew it was this register that should change because of how the instruction operated. Just give a couple more examples of how this works. So if you have some state like this, where a quarter of the time it's in 0, 0, and 3/4 of the time it's in 1, 1, then your branching isn't 50-50 anymore. So if I measure the first qubit, that's the left one, and I put it in classical register 3, then I either end up here or I end up here. You can also get scenarios like this, where the qubit that's on the left is definitely in the 0 state, but the qubit that's on the right is in some kind of superposition. So if I measure the qubit on the left, I didn't actually change anything, because I already knew that was in 0. Questions?
I don't like the indexing, actually, because when you said measure 1, I'm thinking about the second qubit, because I think it's 0 and 1.
Yeah.
0 indexing.
Yeah, so the question was about whether or not the 0 indexing, left or right indexing. It's a convention choice, and I can send you the paper. It's kind of it's got a cool title. Yeah, go ahead.
Do you do multi-qubit measurements, like bell pair measurement?
So in our systems, we do them qubit by qubit, so we don't make multi-qubit measurements. And the language, it's kind of not specifying how it would happen. So in the language, you just have measurements in the computational basis. And you can express other measurements that way too, just with pre or post pre-rotations. But we don't naturally measure in other kinds of bases. So again, if this is the kind of general flow that you should have in mind. I hope that was useful. I want to enlist you, because I know you all actually already kind of probably know a lot of this material, but I want to give you some tools to help explain it to others who might not, because it's not easy, having tried a lot. So there's this abstract model that's actually behind all of Quill. That was kind of a general introduction, but there's a formal statement of how Quill works as well, which is that it operates on something called a quantum abstract machine, which is a finite state machine. And there are 3 types of instructions. There's the quantum instructions, there's classical and measurement instructions, and then there's these control instructions as well. And this is a small Quill program that has examples of each that we'll just step through as state transitions. So at the beginning, we initialize into the 0 states. So the quantum memory has a state, the classical memory has a 0 state, and then there's a program counter that starts at 0. We apply some quantum instruction on the qubit 3, as it says in this example, a Hadamard, and we change both the program counter, which increments by 1, and we change the quantum memory, because we've changed the wave function. Then we can do a measurement, and this measurement's going to change both the quantum memory and the classical memory, based on how it branches. It's also going to change the program counter again. Then there's another kind of instruction, and this is like it's called some classical control flow instruction, or in this case, we do it as a jump instruction. So what this says is, when the classical register in bit 5 is 1, then jump to the label end. And so somewhere else in this program, there's like a little syntax for label end, and it's going to jump to that. Now, if you're lucky, then the programmer who's done this has put that at the end of the program, but sometimes it's not. So all that does is change the program counter, and that moves you somewhere else. And this kind of classical control comes up in a lot of different types of applications for quantum computing. It comes up in doing error correction. It comes up in doing hybrid algorithms, these things that I'll be talking about some more soon. It comes up into tricks, these things called repeat until success circuits, which some of you might have heard of, and making compilation better. And so these kind of classically controlled statements are actually really, really fundamental to how you use quantum computers in the near term. And they tend not to be formally specified. So people typically, before this, would talk about quantum circuits, and they'd leave out all of this kind of classical instructions. And these are actually very, very important to have. And there's a whole bunch more kinds of instructions that interact like this. So you can do things like have a gate that's parameterized by a bit of classical memory. And I'll talk a little bit more about that. Yeah.
How is the jump when not a measurement?
So the question is, how is the jump when not a measurement? It's not doing anything to the quantum data. So it's only looking at the classical register. So the 5 has brackets here. So it's looking at a classical bit.
So it's just like if-else statement.
Yeah, it's like an if-else statement. You can do loops and wrapping. It's a go-to, right? Yeah. Cool. Yeah.
I know that IBM's QASM, they also have a classical if instruction in the language, but it's not actually implemented. Last time I checked. is your actually implemented?
No, we don't. Yeah, we don't support everything in hardware now. We're
It's
working
not
on it.
supported in hardware.
No, it's not. It's going to take some time to get all this shared memory stuff built in, but Quill is like we think of that as a roadmap for how we're going to develop the hardware, which is not just a roadmap for the quantum part. It's also a roadmap for the whole system and how you program it. And the simulator that we built that I'll talk about a little bit accepts Quill, so it does all of this branching and classical control and stuff like that. So you can test it out. And we've got some more features around this are coming soon. So long term, I think you're going to eventually have programs a little bit more like this, where you have quantum instructions and then some measurements that deposit into classical memory. This makes a bell pair and then measures it. And then you can have a wait instruction. It's another kind of instruction in Quill, where the quantum processor will stop, and you'll hand off to maybe some C code or something happening on the classical processor that just looks in this shared memory, does some computation, and then tells the quantum processor to continue. And maybe this classical processor will deposit more information into the classical memory, and then the quantum chip will look into this memory to decide what to do next. So this handoff procedure of making quantum processors work with classical processors is really important to formalize and get right.
How does that affect quantum speed up?
Complexity, because the benefit of quantum computing is to reduce or increase the speed of calculation, right? But like log n. So if we're passing it back and forth to classical, does that slow everything down? Is my question. How much would that slow it down?
That's a great question. So the reason we do this is to get more out of quantum chips that still have noise. So yeah, so if you don't do something like this, then you're going to need to wait a very long time for a very big, perfect quantum computer to see it speed up. If you do, then there's stuff you can try today. No, we don't have speed. We're not speed up size yet, but it's getting there. So the whole environment that we use to program this stuff is called Forest. There's a lot of pieces to it. There's different kinds of backends. So there's that 19-qubit chip that I talked about. There's this simulator, which we call a quantum virtual machine, which is an implementation of the abstract machine that does run all the different control flow operations. There's also other kinds of fancy features in there that I encourage you to check out. And then the dev kit's built around that. So there's Python libraries. There's examples of hybrid algorithms that I'll talk more about. And the whole thing's open source on GitHub. And we do this because we want other people to help figure out how to work with these machines. I think the people ask, are we going to have a quantum programming language? And I sometimes answer that we're not ready for one. We need to understand the applications better, and the best thing to do now is to get the instruction set right, because that means we know what hardware we're building up, and we know what algorithmically we can start to target down so the hardware and software can meet, and then we can start to do some higher level stuff later. But if anyone has really good ideas of how to do higher level quantum programming, let me know, and please work on it. So what do you actually do when you want to program on one of these systems? And so there's an API, and you can run this stuff today. You have your PyQuil code. So PyQuil is Python Quill, which is sort of a Python library that easily lets you generate Quill code instead of having to do it all by hand. It's got a lot of other features in it. You generate the Quill code from that. It runs over to that rack that I showed you, that classical control rack. And that turns it into RF and DC pulses that hit the chip. Quantum operations happen, and then it comes back and gets sent back to your computer. So when we say we're doing quantum computing, we're doing a digital to analog to quantum to analog to digital process. Which is interesting at every single one of those levels. So in particular, all those analog to digital conversions of signals need to be learned and calibrated, and if you ever go into an experimental lab, that's a bit of a complicated thing to do at scale. If you want to play with this and you want to work on it, you can just sign up for free, and you get an API key, and you can run in the programming model and play with stuff. So I've talked about this error point before, and this is just to kind of emphasize and hit on the head here. This chance of hardware error in a classical computer only matters when you're at enormous data center supercomputer scale, which we are actually as a human race, but it's not as big a deal as this. And this is optimistic. I mean, this is kind of what we're building towards, having 0.1% error, 0.01% error in the systems that'll be available in the next couple years. So how do we deal with that? Well, instead of just sending a program, preparing a distribution, and sampling from it, we can instead think about tuning that program so that it works even though this quantum processor has noise. So as an example, you can parameterize the program. So this is an instruction that's parameterized. Instead of being a total bit flip, it kind of lets you flip it halfway based on this parameter theta or something like that. And so the model you should have in mind is that, okay, I'm going to send a program that has some parameters in it, get out some outcome and sample, and then I'm going to optimize the result for that choice of theta against some objective function that I care about. And so what you're kind of doing is you're learning what the quantum program should be based on the noise. And this has allowed us to do a lot of interesting things with smaller chips than were thought before. So I'll go through a couple of those three categories: optimization, simulation, and machine learning. Quantum machine learning is a very nascent and interesting field. I think the number of really good papers in this field maybe doubled in the month of March. A lot of these papers are from March. There's a few more that have come out recently. And they all fit into this flavor. So it's everything from trying to replicate how a normal ReLU works in a neural network, to doing just kind of different kind of kernel methods for classifiers. This is another kind of classifier paper where they classified the bars and stripes model on an ion trap quantum computer. But they all fit in, you'll see this diagram looks the same, they all fit into this idea of doing hybrid computation, where you run some quantum program with parameters, you optimize them over an objective function, and have it come back. And there's a lot more work to be done in this field. So the state of this field is pretty much, we didn't think we could do machine learning on noisy quantum computers. Now we realize we can do it, and we're trying to figure out whether it will be better. That's sort of the state today. And when it will be better is the other thing. How many qubits do you need for it to be better? The second big area is in quantum simulation. So this is an algorithm called the variational quantum eigensolver that's arguably the first real important and impactful hybrid algorithm coming out of the Alanis Baruguzik group and Jared McLean's work there. So the way this works is you start with some description of a molecule. So what you're going to do is you're going to try and find the ground state energy of the molecule, which is useful for predicting chemical properties. You start in some second quantized form, and the first step is to transform it into some representation in qubits. And there's ways to do this. You turn it into Pauli operators. This is the example for H2. And then what you're going to do is you're going to optimize this Hamiltonian, optimize over this Hamiltonian to find the lowest eigenvalue. And you do this with a basic principle which just applies to any kind of Hermitian matrix. So this is called the variational principle. If I have a Hermitian matrix H, and I can actually take an arbitrary matrix and make it Hermitian just by popping it on the diagonal with its transpose, then if I take the expected value of that Hermitian matrix with some vector, I know that it's always going to be greater than the smallest eigenvalue of that matrix. So the insight, and it's sort of it's an intriguing insight, but it's not that complicated, is instead of finding the expectation value with a single vector, you do it with a family of vectors. So you take some parameterized family of vectors, let's say phi of theta, and every time you calculate the expectation value, you know you're bounded from below by the eigenvalue. So I can calculate the expectation value for theta 0, and then pick another theta 1, and then pick another theta 2, and sort of minimize and optimize to get some minimization over this, which will eventually let me converge down to the smallest eigenvalue. This is impressive because H can be an exponentially large matrix in the quantum case, and finding eigenvalues for that can be quite difficult. Obviously, there are all of the gotchas and captchas that I talked about earlier about how do we represent that matrix. And it's got that same sort of general flow. One other thing I want to point out here is that in this paper, one of the interesting things that they found when they looked at the Hamiltonian was that not all the terms matter. So the terms in red are the ones that actually affect something that's not just a phase in the computational basis. So it's just the ones in red that matter. I mean, the terms that have ones in red that matter. So that means that instead of needing, what is it? I think it's 4 qubits, you actually only needed 2. And the general point here is that when you run quantum algorithms, it's not just the quantum programming side that really matters. It's also about how you, at least in chemistry and also in the other domains, you need to understand how to map your problem efficiently to improve the number of qubits that you require and to make it work earlier and better. So this has been run in a couple different benchmarks over the last few years. The first application was to a group from Bristol, an optical quantum chip. So this is simulating H2, where you're changing the bond length between the 2 hydrogen atoms. That's the x-axis, and the y-axis is the energy. So pretty noisy. And then a few years later, a Google superconducting qubit chip, like the chips that we make at Rigetti, improving the accuracy of this a lot. So this red curve here, or sorry, the blue curve with the blue data points is using what's called the phase estimation algorithm, which is not strictly a hybrid algorithm in the way I've been talking about. It's an older one, still very interesting. And the red curve is the hybrid algorithm. And so it's a very clear demonstration that this is a kind of algorithm where you can decrease the noise. Recently on the cover of Nature, there was a result from IBM. They worked on an 8-qubit or 7-qubit processor to do a couple other small molecules and small molecule benchmarks. Now, I want to be the first to say that if you show this to a quantum chemist, they're not super impressed with necessarily with the accuracy of the curves at the bottom. There's not that many data points, but it's still impressive work because this is a start. And what I'm really excited about with this kind of benchmark is we're talking about what a quantum processor can do, separate from all the details of what are the error rates, how many qubits do you have, how do they connect. This is an application level benchmark. So when you have a lot of different types of quantum processors, you can run these molecular benchmarks and you can compare them against each other. Sure, maybe they're not all as accurate as the theoretical result, but I can compare one processor to another and understand if I'm getting better. And so in the next few years, I think we're going to see a lot more benchmarks like this. And I'm pretty excited to see more. I'm going to talk about another one here, actually. The third application area is in optimization. So there's an algorithm called the quantum approximate optimization algorithm, which is also one of these hybrids. It works in this model where it can tolerate noise. And it works on a binary constraint optimization problem. So here I've got some bit strings, and I've got some list of constraints. And for each constraint, if I pass in a bit string, I'm either going to get 1 if the string satisfies the constraint, or I'm going to get 0 if it does not. So I have some set of these constraints, and my job is to find the bit string that either maximizes or minimizes the value of this constraint function. So it's pretty general. In general, it's NP hard. And well, I guess we don't have a chalkboard. But the idea here is not that quantum computers are going to solve every NP hard problem. It's instead to recognize that classical computers, heuristically and in practice, can solve some classes of problems that, in theory, are actually very hard. So maybe that quantum computers can solve a different subset. So there's some Venn diagram of what we can do classically and another Venn diagram of what we can do quantum mechanically in heuristic form, and there'll be some new region that we can push into. But we're not going to solve all NP hard problems. I think that's unlikely. So this general abstract framework can be applied to a couple different type-specific problems. Oh, this should just say clustering. I'm sorry, it's just a clustering algorithm. Everything from the traveling salesperson problem to logistics and scheduling, check this reference, to Boltzmann machine training. This is a result from our group, from some of my colleagues. They ran this algorithm on our quantum chip. And I want to draw attention to it for a couple different reasons. So what we're looking at here is the number of steps in the optimization procedure. And in the y-axis is the probability of you having found the correct answer by that step. And the problem is, I'm given some set of points, and I need to cluster them into 2 clusters based on some Euclidean distance similarity or some other kind. Actually, we generalized it, but some other kind of similarity metric. And that's a whole another talk. But what you see is that if I run on the quantum virtual machine, this exact version of a quantum computer, I get the answer after maybe like 22 optimization steps. And then if I run it on the 19-qubit chip, there's clearly a gap that's caused by the noise that's in the chip. And we can actually quantify that gap. We can see it right here. And then we, of course, did the thing of comparing it against the best possible classical algorithm, and wanted to plot that on here too, which is random sampling, which is not the best classical algorithm, but it is a good example. And so what this is showing is that the 19-qubit chip is, while it's not perfect, it's also not just noise. You're actually doing better than you would if you were just sort of sampling from the space. And we need a lot more algorithm examples like this, because what you can say is you can see exactly as the processors get better how they'll start to approach this limit. And as we look at other kinds of classical examples, we can disambiguate what's happening on the chip from what you could do as a classical solution. So again, I think this is another embodiment of what you get as an application level benchmark of how processors perform. And we'll be seeing a lot more of that in the next few years.
Can I ask a quick question?
Yeah, please.
Are there sort of finance-related algorithms that are in this optimization space? You've got 3 examples, well, 4 there: traveling salesman, scheduling, gaming, Boltzmann. In terms of like applications in the finance space, are there ones that would fit in that area?
Some people are looking at portfolio optimization. This algorithm is similar to the way quantum annealing works, and so any quantum annealing application can actually be digitized and generalized and done this way on a gate model machine. And there they've done some portfolio optimization stuff, and I think I can find some references if anybody wants to know more. But I will probably, I bet someone, I'm not writing it right now, but someone is almost certainly writing that paper right now on one of the gate model machines that's up.
Thanks.
Whether it has business value, though, is a different case. Different question. So these algorithms are not that hard to write. So Forest, it's in Python. This is QAOA. It's pronounced QAOA for some reason. This is the quantum approximate optimization algorithm. This is most of it. There's a little bit more in the optimizer. But it's pretty clean. You import some things, you define the graph that it's operating on, and you can define the algorithm at a higher level than just the gates. So one thing that you might notice here is there's actually not any gates explicitly. There's no quantum instructions, no classical instructions. It's all done at the level of Pauli algebra, and then that automatically is converted by the library down into instructions that can run on the quantum processor. And another neat thing about the library is all you do is change one line to flip between the QVM and the QPU. So the QVM being the simulator and the QPU doing the real chip. And you just change these 3 letters. Well, 2 letters, actually. If you change QPU to VM, it'll run on the simulator or go back.
So this is quantum annealing, is it?
No, it's all gate model.
All right.
So everything I've been talking about is gate model.
Sorry. What's QOA?
It's the quantum approximate optimization algorithm. Yeah.
14 lines.
Yeah, it's not so bad. So it's another talk to explain how it works, but it's approachable. And you can, from this, you can generalize it. You can try different drivers. If anybody knows the algorithm, you can try a lot of stuff. So a few of the major open areas in quantum programming that I don't think a lot of people are working on, and I'd like to highlight a little bit, are these. So one of them is debuggers. So when I first worked with our colleagues to write the variational quantum eigensolver in our group, we had a very serious typo bug. We had a Y gate where we should have had an X gate. Simple thing. We didn't find it for 9 months. And the reason is that the classical optimizer was optimizing around the bug. So not only does it optimize around noise, it also optimizes around bugs. Which means that we found it per chance, but what would have happened is it would have worked just fine on small examples, and then once the optimization started to get really hard, it would have failed for a reason that we couldn't understand. We would have thought it was the optimizer, but it wasn't. It was because there was a bug. So this problem of debugging probabilistic and empirical code applies to classical machine learning, and it also applies to hybrid quantum programming, where you have sort of classical machine learning as part of what's going on under the hood. How do you write a debugger for that? How do you debug it? Some of the proposals are to use languages that are strongly typed and be more formal, but how are we actually going to do this? There's not that many people thinking about it. Another is to think about optimizing compilers. So when we write things in the quantum abstract machine model, we're not thinking about how the qubits are connected to each other, which matters to what gates you can apply. We're not thinking about the error rates and noise. And we're not thinking about the fact that not all quantum chips support all gates. So they always support some universal gate set in the same sense that NAND is universal for classical computation. The chip will support something that's universal, but there's overhead to converting between them. So we need to build compilers that will do this kind of optimization, because every factor of 2 matters in the near term when your error rates are as high as they are. Next, we're going to need some application-specific packages. So quantum programming is something that is exciting for some people. They want to learn a new type of programming for a lot of the reasons I talked about at the beginning of the talk. But we need to make it accessible for those who are operating in their domain. So one of my favorite examples of this is a project called Open Fermion, which is a collaboration between us and Google and a bunch of academic groups. My colleague Nick Rubin has worked on this a lot. And what it does, and sort of what it's aiming to do, is make it so that someone who's a quantum chemist, who doesn't know quantum computing, can use data structures that are familiar to them and natural to run molecular simulations on a quantum computer. So they don't actually have to learn that much quantum computing in order to do it. It's not all the way there. It's still pretty technical. But I think that's the right goal. That's the right ambition to have for application-specific packages. And we shouldn't just have it for quantum chemists. We should have it for a couple different areas. We should have it for ML. We should have it for optimization. We should have it for specific types inside of each of those, so that we can expand the types of people who are doing the work that needs to be done now. The second one is on adoption and implementation, and it's exactly that same point. So how do we expand who's working with these problems? There's a lot of papers out there that are released with results that have no code. And I think this is holding the field back. We're all trying to figure out how to do quantum programming together. And if we don't share libraries and build things that people can work with and stand on each other's shoulders, then it's going to take a long time to make quantum computing useful. If we work together, release code, make integrations, so for example, Forest integrates with Open Fermion through this little package. And just as an example call out, there's a programming language developed by Oak Ridge National Laboratory in the States called XACC, which integrates and calls Forest, but also calls other libraries, and it's open source. And we can learn from each other about what works and what doesn't work in quantum programming when we actually produce these implementations and show how things happen. I mean, we had our first hackathon a few weeks ago. We had people fly from Japan and Canada, and there were high school students and researchers on the papers that I showed here, all working together on stuff. And that was extremely exciting. It showed that we got far enough that quantum programming is easy enough that you can sort of hack on it for a weekend. But there's a long way to go to making it something not hundreds of people or 1,000 people in the world think about. What does it take to make it so that 1 million people are programming quantum computers? Right? What do we have to build? So I hope I've been able to give a little bit of an answer as to why one might want to program a quantum computer and how you might go about doing so, using hybrid quantum programming in Forest and Quill and some of the processes we've made available. So kind of the last question is to put it back on you, which is what are you going to do with quantum computers and how are you going to apply them? Thanks.
Hi there. Some people talk about the noise in the, say, the problem. You encode the problem into some form. You process and compute on that problem. Then you decode the problem that you have. In order to detect and correct qubit potential noise, how many qubits will be needed to do simple calculations which match classical computation in contemporary machine learning, for example?
Okay, yeah, there's a lot in that question. So I think part of it is you're asking how many qubits do we need in order to start doing error correction? And that's a subtle question. There are some small codes. You can start testing codes with 9 qubits, a 9-qubit Steen code. There's smaller codes that you can start to benchmark. But the number of qubits you need to correct errors depends on how robust your algorithm is to errors. So if you were trying to run Shor's algorithm, then a recent, well, not that recent now, I guess it's a few years old, one paper did a study of how many qubits you might need to do Shor's algorithm to an appropriate tolerance to factor a 2048-bit number. And the answer was 1,000 to 1. So you needed 1,000 qubit overhead to decrease the error rates for that particular algorithm. But if you want to simulate H2, it's 1 to 1, even from the systems we have today, right? And I think the way that error correction will get introduced is gradually. So the way to think about it is we'll start with these algorithms that are sort of robust to noise, and we'll improve the individual qubit error rate, and we'll start to add overhead for error correction gradually as it makes problems better, or solved better, I suppose. Does that make sense? Yeah. Cool. It's one of the things that I think you'll see us and others start to benchmark and test over the next couple of years, but not implement at large scale in a couple-year time frame.
So with a lot of machine learning problems, what we do is we use stochastic optimization methods. So we don't care that it's a noisy calculation because it's cheap. But what we need is that that calculation is unbiased. And if it's unbiased, if those errors are unbiased, we can have a schedule where we make smaller and smaller steps, and we can guarantee conversions. So I think for quantum computing, one of the things that's going to be more important than noise is that noise is unbiased. Yeah. So I was wondering what thoughts you had on that area.
Yeah, the topic of quantum noise is extremely fascinating. You have types of, you can get entangled noise, right? So the fact that you can actually do error correction on quantum systems is in and of itself a pretty fascinating fact. The types of noise you have in your device, some can be compensated for, some can't. So for example, we have some features in Forest which allow you to compensate to some degree for measurement error, where we measure a qubit to be 1, but it's actually not at 0. And you can kind of wrap that, and you can do some statistics in the classifier and actually compensate for that by sampling more and stuff like this. Other types of noise are harder to compensate for. So incoherent, non-Markovian noise is like this stuff. And there are some schemes, people work on them. There's even some companies that have some ideas for schemes that can help you kind of deal with these sort of problems in your systems. But there's no there's no gimme. So I think we'll start. One thing people are working on a lot is benchmarking quantum computers and benchmarking their noise. And so we'll see a lot of that in the next, let's say, year or so, where people characterize the different types of noise. My worry with that is it's going to be super esoteric, and like I'm going to understand those numbers, but like they're not going to work for a programmer. So we'll get there.
Thank you. So thank you for your presentation. And I have two simple, maybe just short question. First is, did you try to use quantum computing to solve some like long NP problem, like non-polynomial problems? And second is, how is the scalability of the quantum computing?
So maybe I'll take the. So I don't know a lot about what you mean by non-polynomial programs. Did you say non-polynomial programs?
Yeah.
Or what's an example?
Just some traditional.
Like instead of linear programming. I haven't worked on that, but there might be some papers that I can think about.
Okay.
So traveling salesman's approach
Yeah,
to,
yeah,
for
yeah.
example,
Okay, great.
NP.
Oh, I thought you meant NP complete. That's what. Oh, that's what you mean.
No, just NP problems. Yeah.
Yeah. So no, exactly. Yes, a lot of these are NP hard problems, particularly in the optimization
How
space.
is the performance like compared with traditional computers?
Yeah, so we just benchmarked it against random classical sampling, so it's not that impressive today. But the question is, how is this going to scale? And in order to answer that question, you can't prove it. It's empirical. It's like in machine learning. You need to actually build the systems and start to test them. So we're going to have this interesting regime happen where we're going to build systems that are not able to be simulated, and we need to experiment with them to figure out how they're going to be benchmarked and how things are going to scale. So and then that leads to your second question: how are these actually going to scale?
How about like a scalability of the quantum computing?
Yeah, exactly. So I think in the next 3 to 5 years, the kind of fridges and the systems that we're working on, the thing I tell theorists who are thinking in that time frame is think about something like a few hundred or 1,000 qubits where you can apply maybe 1,000 gates. What can you do with that? So that's 1,000, 2 to the 1,000 by 2 to the 1,000 matrix multiplications at 100 nanosecond cadence. And there's all these caveats, but that's a pretty fascinating resource to figure out how to exploit. I hope there's a breakthrough where we go even faster, but there's no real new science that has to happen to get there.
Hi, yes, the code that you showed earlier, the one that's 14 lines, does that actually compile to some intermediate form, an abstract form, as in line with what you said about an abstract machine, before you transform it into Quill? Because I think that intermediate form would help others understand how you synthesize, your high-level program into actual gates.
Yeah, so we don't actually compile the Python into Quill. It's a builder pattern is what that library actually works as. So you generate the Quill as like a string. So that code that I showed you goes straight to Quill. There's not another intermediate representation in the middle. There are other kinds of data structures there based on the Pauli algebra structure, the higher level mathematics, but it goes straight to Quill, and that's what gets sent to the API.
Thanks.
Fascinating talk. Thank you very much. I think you really brought it to life. A couple of questions, hopefully not too stupid. One is, how does your 100 nanosecond 2 to the n times 2 to the n and small I/O compare to another big development, I suppose, which is like biological DNA-based computing?
Oh yeah.
And the other thing is, in terms of because you obviously, as you say, a big physics and computing person. The way they solve I know it's a different sort of thing, so it might be a completely stupid question, but the way they solve the noise problem for the laser interferometers they use to detect gravitational waves, the LIGOs,
yes.
Sub-quantum level noise, the way they did it is amazing. And I don't know whether maybe is there a route to the other news that you're fabricating on
yep.
silicon still, not light. I mean, I don't know. Is there something in that area at all?
Well, so I'll talk about the second one. I really don't know much about DNA computing. I'd like to. That'd be fun. What I do know is that there's this exponential law that we have in quantum computing. I don't know of any technology that has something like that. That's something pretty special. It doesn't apply to neuromorphic. It doesn't apply to DNA. So I think it's a special thing about quantum. But to your second question, quantum sensing and doing sensing of systems beyond the classical limit using quantum effects is a really cool area of study. It doesn't just apply to optics. It's something that just applies to any system. Actually, one of my colleagues who works on our our hardware team, Alexa Staley, worked on the LIGO experiment on that stuff. She works on our fridges now. In addition to the quantum processor that's in our fridge, there's another device that's also a quantum device. It's called a quantum limited amplifier, also made of DUF, Josephson junctions. What's great about this technology is you've heard of the Heisenberg uncertainty principle, which is uncertainty between position and momentum. There's also a signals version of this, or a noise version, which gives you a fundamental floor on the amount of noise that there is. These amplifiers are called quantum limited because you can see noise that's due to the Heisenberg uncertainty principle, which is fantastic, because that's what makes all this stuff work. And so that's actually how we read out the chips. And that technology has been around almost as long as superconducting qubits. It's sort of been developed part and parcel. If we didn't have those, we also couldn't do this kind of computation.
If we go 5 or 10 years in the future,
great.
Would we be seeing, I don't know, libraries of quantum circuits that could be put into interesting hybrid quantum classical algorithms to solve problems? And this library says, if you want to really optimize this problem, choose circuit A, maybe put together with this, circuit B. Is that how you see things? Or how
and by circuit, you mean the processor, not like the program quantum circuit? This is like a degeneracy, unfortunately. You mean like the hardware, right?
Maybe
yeah, okay.
The hardware, but also how you realize the circuit with the hardware in this. Do you see that we'll be developing these libraries that maybe people with less quantum background will understand, oh, well, if I pull it off the shelf and put it together, that will give me some speed up or address a larger problem?
Yeah.
Is that the way you see it happen or not? Or do we have to sort of take the paradigm differently and think of, actually, you just got to do quite an awful lot of first principles work of mapping the problem to determine which...
No, somebody's got to do that first principles work.
Yeah.
But don't make people do it every single time. Like once you do that mapping, you can build it into a module that someone else can use as a black box or more as a black box. So I agree with you entirely that in 5 to 10 years, there are going to be examples where you don't need to know what's underlying to make it useful. And we have examples like that now, like the Open Fermion project is working on that for quantum chemistry. So your other question, I think, which is that, if I understand it correctly, will there be systems that are optimized for specific problems, and will someone help me pick which? I guess pretty likely, actually. We haven't done that yet. We've been working on a basic chip architecture and platform to test a lot of things. But one of the advantages of being a full stack company where we make our own chips and we fab them and we design them ourselves is if someone comes to us and says, make this chip topology, make these changes, and it makes it like a quantum ASIC, where it's specialized for a particular kind of problem, and that's a valuable problem, we could do that. That's actually not that hard. We just need to be motivated to go in a particular direction. That's what we're trying to figure out right now. So I think in the future there's going to be several different kinds of technologies that work differently or better for other kinds of things. It's just like we have with computing today, right?
Actually, I've got a question myself. I've got
Sure.
a double question. I know they're popular today. So the first one is, on one of the slides you mentioned climate change and carbon sequestration.
Oh yeah. You're right.
Obviously, I don't expect you to know loads of stuff about that particular thing because it's an example, but I'd be curious to know if you've where you've seen that or what kind of things that applies to. And the second question is a very short one. Why call it forest?
Oh yeah,
Where did the name
that's a
come
great
from?
one. So for the first one, these are related questions actually. So for the first one, this nitrogen fixation problem, we take nitrogen out of the atmosphere and use a catalyst to turn it into ammonia. Like, there's also there's systems that do carbon capture. Plants do it. Could we find a very efficient catalyst for doing that reaction? Is the high level thing. I'm not an expert in that field, but we would love to work with companies that are much more expert in that area to help attack this problem, right? And that leads to your second question, which is why this is called forest. There's two reasons. One is, especially about 5 years ago when I was looking at this and getting started, when people thought quantum, they thought scary cybersecurity, artificial AI, Skynet thing, which is not my view of quantum computing. I also don't think that's how quantum computers are going to emerge, and that's also not how they're going to be meaningful. Quantum computing is about taking what's in nature already and using it to solve problems that we care about. It's doing things in climate change. It's doing things in designing fertilizer. And calling it forest is reminding us that it's about nature that we're working with, and this is a kind of a natural technology that we're trying to exploit better. So I like that idea. And the second one is that we need to build an ecosystem. So this isn't, while we do a lot of things, we make the chips, we go all the way up to the hardware and the applications. We know that we're not the only company, and we're not going to be able to do all the problems. So this is open. The forest ecosystem is open source for that reason. We want a lot of people to participate in it, and we want it to help and grow. So that's kind of what played into it.
Thanks. Great answer.
So we often talk about timelines of quantum
Right.
computing. I think sometimes it's more useful to think in terms of milestones. So quite often quantum supremacy gets talked about for good or bad, but it's a milestone. Do you have some milestones internally that you consider to be indicators of how the quantum computing is progressing?
Yeah, I'll talk about a couple of the main ones, and then maybe a few things that are not talked about as much. So in terms of the main ones, quantum supremacy is an important milestone. It's just not as important as it sounds. It's a big proof point that the technology can do something that no other tech can do. It doesn't tell you basically anything about application, because the benchmarks to show supremacy are very esoteric. They come from nuclear physics or quantum chaos. So it will be a good benchmark to show that you can build systems that do something, but not that you can do something valuable. The next milestone to look for is when someone solves a valuable business problem. So a problem that I get some ROI, I compare it to a best-in-class classical solution. The point here is that I think people, especially theorists, think that the only way to beat the kind of current classical method is to be faster or to be more accurate. But those are only two ways of getting value. Like, it might be the case that you use a lot less energy. This is actually, I think, something that might be very, very likely on the machine learning side. So maybe we just do as well as regular computers, but we can, instead of having a huge data center, we have one of these quantum processors actually help out. And if you save 2% of the energy that Google is using to train neural nets, that would be a big deal. So we call that quantum advantage instead of quantum supremacy. It would be very entertaining for me if the reason people use quantum computers was because it was easier. That would be another way. And it could happen if we have a lot of help. So that's kind of the second big milestone. And that's going to be a limited application area first, and then it will broaden normal technology adoption. Other kinds of milestones that I alluded to in this talk are when we have application level benchmarks that we all agree on and that we're using. So if you look at GPUs today, then they tend to have these suites of they run a bunch of Photoshop on it and they compare how they work. What's the quantum equivalent of that? So when you start to see those benchmarking suites come out, then we're understanding a lot more about applications as well. Even if they're not better, we're still coming to an understanding of those benchmarks. That's one. And a second is how the ecosystem evolves. So right now, there's us, and then there's Google and IBM and Microsoft, people making these systems. And then there are some companies sort of doing consulting and software. Quantum computing is a whole nother kind of version of the entire computing industry. And there's not just like hardware and software and people that do both. There's all these layers. There's a whole industry in classical computing for making software to help you design chips. Cadence is a big company. They make a lot of money. So when we start to see some of those other areas of the industry emerge as independent companies in their own right, they can start to address different layers, and we don't have to do everything as integration. That's going to be another really important milestone as well that people don't think about as much. So I wanted to throw those two out as food for thought. Everyone wants to know. So in terms of like when I think we're going to see those first limited quantum advantage applications. It's I think 3 to 5 years. Is the timeline.
So my question has to do with networking. I mean, it's so far I've seen a lot of people talk about quantum computers, how the quantum state stays inside the computer and then you turn it into classical and read it out. But is there scope for actually having communication between different nodes that in the quantum domain?
There is scope. It's just hard. It's even harder. Like you've got like 2 problems now. Like I've got to make quantum computers that work, and I've got to like make them be quantum in between. There's a big UK government quantum technologies project. They invested like £270 million in quantum technology a few years ago. One of the hubs is in Oxford, and they are working on a quantum computing system where you have these ion traps connected by photonic links. So it is actually this multi-node sort of networked system. I'm certain that's not going to be the first way we build something that works. But in the long term, it is possible to make quantum links. It's just really hard, and the error rates are high, and the post-selection is really intense, so it takes a bit of time. But yeah, one day it should be doable.
I mean, one of the immediate problems that springs to mind is that if you want a network that has addressing, then you sort of have to look at the data as it comes through. And so
right, yeah, you can't do that.
So, I mean, I don't know how you would separate like the address on a packet, on a message, from the state inside the message. Or...
Yeah, so what they do, this is I'm sort of analogizing a little bit, but what they do now is they just make multiple copies. So they make one that, like they make 2 entangled photons, one of which you measure to see if the other one is there. And then this one gets destroyed, and then you know the other one was there. And so you could like have the address be, and you could look at the address by destroying one and keeping the other going. The overhead for that's pretty rough. So again, we need to find some other better way of doing it.
So yeah, is Rigetti making any money yet? Or yeah, are you just a lab?
Great, we are not just a lab. We've never been just a lab.
Okay.
So one of the fun things about working at Rigetti is while this is a technology that's going to take a long time, relatively speaking, it's not a SaaS company. Well, actually it is. I mean, we have quantum as a service, but it's not an app, I say. We're focused on making a product. And the goal of this, we as a startup, we measure success by the value that we produce with that product. So I'm not going to disclose our financials, but it's going to be an exciting couple of years.
When are you going to run a hackathon in London, and how do we sign up?
Well, I think we were just talking about this beforehand. Maybe you guys could host it here. We could have some remote stuff. If you want to do you don't need my permission to do a hackathon. Just do it. The tools are available. You can sign up for free. You can get the libraries. And if stuff doesn't work, you can yell at me or my colleagues, and we'll help. Do it. Yeah. We can share best practices of what we learned back in the Bay.
Fantastic.
Happy to. Yeah.
So machine learning and AI kind of went along for a while, and then the thing that made it very easy for people to understand was some guy started to apply it to computer games.
Right.
And everyone got it. Right, straight away, you didn't need to explain it anymore. They could see that it could solve computer games, and then they could see how it applied to their problems very easily. Do we have a similar thing for quantum computing? It seems to me it's much tougher to get that barrier and that explanation across.
Yeah, it is tough. There are some quantum games. There's a guy named James Wooten who's at the University of Basel who makes some cool ones. He made a quantum battleship game. It's a pre-release. I'm working on an app. I have a mobile game. I did this at the hackathon. And it will be at some point on the mobile game store, trained on a quantum processor. But you can build games. So that's sort of one interesting thing to think about. And it's a great way to learn quantum programming, and I'd encourage people to think about it. But your general point of needing an application where you don't talk about the fact that it's quantum, you're just like, here's what it is, and people get it. We're not quite there yet. If anyone has ideas, we work on it every day.
Actually, I had one other question about input-output. You said about input and output is very limited for a lot of the applications. Seth Lloyd was the person who gave the last talk. I asked him basically the question, isn't that quite a big bottleneck, the input and output? You may be able to do a huge amount of work inside the computer, but if you're limited on your input and output, that can be quite constrained on your, well, for machine learning, you typically have petabytes or terabytes or huge amounts of data input and possibly output. So how does that correlate with what you're seeing there? I mean, his answer was, well, you could supposedly build a system where your input-output was photons on a light beam, and you can basically input gigabits worth of data huge amounts of data, the limit is in terms of sending data into the quantum system. I think maybe the problem then was what happens to that data once it's in the quantum system and how quickly that can be turned into a useful calculation. So
right, yeah, that's hard. I mean, you can always send. I mean, if you just send photons in, you're sending data in. But like, are you controlling it? Is it still quantum? Like, can you use anything like that?
Yeah.
So I'm not sure I agree with Seth's answer there. I think it is a problem. So big data problems where you need real-time computation on big data, like not what you should think about quantum computing. There are some approaches where you do things where you take the data space you're working on and you do like an autoencoder to make the data on a smaller feature space and then try and learn it on a smaller feature space and then bring it back. But you're not going to be feeding terabytes of data into a quantum computer anytime soon. So you need to have a different kind of model for how you're going to work on stuff.
I mean, even megabytes or gigabytes is a long way off.
Yeah, it depends on how you want to think about it. So you can think about the so the clock rate of these systems is somewhere between 10 kilohertz to like a megahertz or something like that. And then from that, you can figure out how much data you're putting into the quantum program. So it's 1,000 gates, however many parameters are in there, and you can load that at that rate, and then you can calculate. But megabytes might be doable. I think the last time I did this, I also did this live at a talk, which is why I'm avoiding doing it right now. So I'm not going to commit to a particular number.
No, exactly.
But it's definitely not terabytes. Yeah.
Most data sets that are of any use or value are much bigger than terabytes. I think that was the question, right?
Right.
Yeah. So what can we use them for, if not for terabytes of data? I mean, I can think of useful megabyte, gigabyte data sets, but a lot of big data is, terabytes, petabytes,
right?
Like DNA or something.
Yeah,
Genomics.
so those are, I would say, we need to find either some totally new programming technique if we want to address those, or we need to focus on other kinds of problems. So data sets that are smaller, or feature vectors that are smaller, or maybe the thing you should think about is instead of building the whole model on your quantum computer, you have a classical model which works on your petabytes of data and is trained on petabytes of data, and then the quantum processor just works on like improving little bits of that model. Like the data for the quantum computer is the model for the classical data, or something like that. Again, it's a nascent field, lots to do.
Yeah, it just seems like a really, 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 really fundamental bottleneck that nobody really talks about. I think it's a really good question.
Yeah. No, I talk about it every time. Yeah.
So I saw a compelling presentation given at VW in Munich, where they were exploring quantum algorithms to support traffic flow optimization. They were using quantum annealing.
I'm familiar with the work.
And I think it was like in Beijing, 1,600 or maybe a few thousand vehicles going to an airport, and it explored how, if there were 3 choices of other routes or 2 other choices, how it could smooth the flow. That was really quite compelling, but it's still quite a small problem. Yeah. So I suppose the question is, if we're looking at that type of traffic flow optimization problem, do we need to wait for Rigetti to come up with several 100,000 qubits to address that kind of problem?
For that one in particular, you might. I mean, so that algorithm is annealing. You can transform it into. You can use the QAOA algorithm for that exact. It's a binary constraint optimization problem, but it does seem to require a few, as far as we understand, a few qubits for that particular one. So maybe a few hundred or 1,000 might be needed, or maybe even more. So the thing though to think about in general when you're thinking quantum computing timelines is if you can find something where the quantum solution is improving exponentially, then it might take a bit of time to get to the intercept point. But once you get there, it will very rapidly just like smash through the classical comparison. And when I talk to people in industry, they kind of are trying to get a sense of this to kind of say, well, if you're not ready for when that happens, someone is going to be ahead of you, not just a little, but a lot very quickly. So there's some prep work to do.
We're looking at a wide range of different types of scheduling problems for distribution logistics, traffic flow, telecoms network optimization, a whole range of different operations management problems. And talking to existing experts who do, with classical techniques, optimizing each of those domains to try and get a feel for how large a problem are they dealing now with the best classical processors they tend to use.
Yeah.
And we're trying to use that as a sort of a benchmark. That's something in each of those different areas that maybe we should explore whether there's an opportunity of using some hybrid algorithms.
Yeah.
And at what point will we beat that threshold?
Yep.
And one of them we looked at is job shop scheduling.
Yep, we looked at that too. Yeah.
And it looks as though, I don't know what it would be like with circuit model, but with the quantum annealer, we're maybe only 2 to 3 generations of quantum annealer away to address the largest possible job shop scheduling problem. That doesn't mean it's going to be faster, but
Right,
to actually
sure.
address the size of problem, or at least match it.
Yeah.
Which probably fits in well with your 3 to 5 years time. That's with an annealer, and so.
And we're a little, a number of qubits is a little.
Yeah,
but we have more control, and so there'll be other programming trade-offs. Yeah, I think that's the approach to think about. One thing that I will say is that there's been quite a bit of work on taking classical algorithms and trying to map onto a quantum computer. So do the same classical thing on the quantum computer, or address the same thing that's hard for a classical computer. Quantum computation is also, it's not maybe just faster, it's also different. So when we've worked with partners or talked to people, we ask them, what's the hardest thing for you? But then you also have to ask, what do you not even bother doing because you know it's impossible? And it's actually those, I think it might be that second category where quantum computing finds advantage first, because there's not 30 years of classical computer science attacking it because people have just given up. And there's a few kinds of examples in optimization like that, I think.
Maybe related, but do you think quantum computing can be used like FPGA or ASIC for solving proof of work for blockchain?
Yeah, I knew that. Okay, I get one question about the simulation and one question about Bitcoin. only allowed to so maybe in the long term, the kind of most algorithms that I've seen in the literature that try and use quantum computing for this in a faster way rely on some version of Grover's algorithm for a square root speedup. Grover's is not a hybrid algorithm, so I don't know how to do it in a way that's robust to noise. And it typically requires you to operate on quantum data, in which case you need some big database of quantum memory to work on. And that's not what we've got. So, maybe when we have a big perfect quantum computer that does Shors, it will be a big deal, which might be 30 years out. So that matters if you're building a currency or you're making a crypto system. But it's not going to be something that we run super soon. Does that answer the question? Oh, yeah, cool.
Great. Is there one last question? Oh, no? Okay. Well, cool. Thanks a lot, Will.
Thank
That
you.
was really
Yeah.
great.